So maybe before I give introduction to the panel, we should introduce our panel members today. So I'll just keep around so that everyone can introduce themselves. So I'm Elena Reshetova. I work for Intel. So I have a history of working various Linux-related security features. My latest focus, maybe for the past 2 years or so, is confidential computing, technologies like CHERI and Intel side. So
I'm James Morris. I previously was a maintainer of various subsystems in the kernel, mostly around security, previously on SE Linux and NetFilter, LSM and others. And for the past, I think, decade or so, I've been a manager mostly of teams, kernel and upstream and security teams. So I guess my representation here is, having some upstream experience. Also, more recently, I've been involved in virtualization-based security in Linux, which is, a virtual approach to some of these issues.
My name is Scott Constable. I'm a security researcher in Intel Labs. So since I joined Intel in 2018, I've had the privilege to work in a number of different areas, one of which has been Linux kernel security, but I've also worked on confidential computing, and in particular, defining the confidential computing architectures, helping to define them for Intel SGX, Intel TDX, and I've also more recently been working on some formal verification of standard protocols.
Hi again. My name is Kevin Brodsky. I've been a software engineer at ARM for almost 10 years now. Did it work? Yeah. Okay. I've been working on, mostly security features at ARM, both user space on Android and in the past few years more on the kernel side. So I worked on a lot on CHERI and Morello, and also on MT memory tagging. And now, as you might have noticed, I'm more focused on protection keys. That's about it, I think.
Hi, I'm Carl Shaw from Codasip. I've been working on Linux for decades, longer than I care to imagine. Mainly in working with commercial companies. So most of that work has been putting in hardware features into chips and devices. A lot of this work doesn't get upstreamed because it tends to be focused on a particular chip or technology. And obviously recently, as you saw this morning, I've been working on the CHERI technology, which is definitely more of an open technology, and what I'm focused on.
okay, so thank you, everyone. So let me just kick out a discussion by just kind of panel level setting for the panel. So the topic of this panel, as you can see in the title, is like challenges and having. Basically, the goal is to have a discussion about the challenges of enabling security technologies which are backed up by hardware mechanisms. And if you take a look on the kind of the history, maybe for the past 10 years in the Linux kernel, so we have had examples of technologies which really had hard time getting into the kernel. And I guess the protection keys you heard the talk earlier today, it could be like one good example. So, the various use cases where it has been tried to be applied, I think we had 4 or 5 different use cases. It's not just been like, an example of technology pushed, uniquely by Intel or x86, Now other vendors also have it, but we still have issues of merging this technology. Another example I can think, I'm more aware of x86 technologies or Intel ones. We had this HLAT technology, which is also like closely related to this use case of protecting the page tables. So, and it's also like, it was a couple of years ago when it was introduced, and still, we had proof of concept code and for the Linux kernel, but it's nowhere near even like being merged or even actively discussed anymore. But from the other hand, it's not to say that it's like for any technologies this way. From another hand, we have had technologies which made it to the kernel, I wouldn't say like easily, but relatively easily. So the discussions points for the panel and the panel members today is that, okay, so what does make a difference when we think about these technologies. Of course, everyone knows the obvious things. More complex is technology, harder it's to merge. If it's hard to maintain, if it touches way too many places, performance, of course, things like that. But let's try to discuss about not so obvious things, because quite often the discussion, the mailing list goes around, okay, how realistic is a threat model? So if we talk again, I'm going back to this protection key example. If we talk about, example of protecting the page tables, we have this threat model that we have, the adversary got or the attacker got the write primitive in a kernel. The counter objective could be, okay, if you got a write primitive and you're able to overwrite the page tables, maybe you can do other things. So, by protecting just the page tables, it doesn't probably buy you as much. So there could be these counter-arguments in threat models. A threat model is important to think about. But there could be other things. So maybe I'll just open it up with this to the panel members. So what people think, what are the not so obvious parts of why technologies get stale, essentially, in their attempts to get upstreamed? Who wants to start?
We have a kind of proverb that I've heard within Intel. I don't know if you've heard it, Elena, that there are no corner cases. When you're defining an instruction set architecture and it's mass market and it's going to be used in personal computers and cars and airplanes, you can't make any assumptions about how it will be used or how it will not be used. And I think even if you go through the whole process of doing the compatibility reviews, building the prototypes, doing the proof of concept, doing the validation, if there's a corner case in the ecosystem and that corner case is not going to be compatible with your feature, that could be an obstacle that will not be overcomable. And I personally had a recent experience with this. My colleague Sebastian and I will discuss this feature tomorrow. But we made an assumption when we were working on a feature and that we upstreamed that, the kernel probably doesn't need to pass around wide floating point values from function to function, right? Who uses a lot of floating point computations in the kernel? Ask a bunch of people, say, no, that's kind of absurd. Well, then you upstream it, and then eventually you get a bug report, and there's some GPU driver that passes around floating point values, and it broke, and now you need to fix the thing. So fortunately, that was just software. We didn't need to go back and redefine an architecture and release a microcode update or have to deprecate a feature. So that was a quick fix, but others have not been so fortunate. That's a little bit of wisdom I hope I can contribute. Anyone else?
So from my experience, I think there's two important angles. One is ABI. So and here I'm talking about in-kernel hardening because user space support is a kind of a different angle. So for in-kernel hardening, if your feature is, let's say, binary backwards compatible in a very easy way, then you have a big advantage. So for instance, on ARM64, there's BTI and pointer authentication for CFI, forward and backwards edge. And for PAC, you can use it in a backwards compatible way, and BTI is backwards compatible. In other words, you can insert those in your binary. It can still run on any hardware. And hopefully the overhead is very minimal if you don't have a feature. So that's much easier to deploy. I think performance isn't necessarily such a big barrier to getting things merged. If your code is simple, let's say, if the enablement code is simple, it might get it removed eventually if performance is too bad, I suppose, but that's probably not the biggest challenge, maybe. But the other point I wanted to mention is just, does your hardware feature fit into an existing framework or not? And I think that's probably the biggest thing, in fact. And so with KP, basically the KP keys proposal that I talked about this morning is trying to define a framework that then could fit protection keys, potentially other features as well. And I think that's really the biggest challenge. So Some hardware features don't really need to have much of a new framework. Some definitely do. I think that's the very big challenge there.
Yeah, I think you touch on that as well. Trying to fit in a security technology with the existing kernel is a challenge. To be able to get it adopted. I mean, I can talk from the recent stuff we're doing in CHERI. Is a lot of the thoughts on how we implement it into the kernel is thinking about, well, first of all, what's going to be the minimal changes in the internal interfaces in the kernel. Because it is quite different from what exists. The other thing is how understandable are each of the changes, because to be able to commit stuff, people have to really, you mentioned the threat model. It's true, you have to understand how the threat model works, but you also have to understand how the technology works and what it's bringing. And for complex technologies, that can be a lot of intellectual capital you have to put in there in the first place to understand the technology. So we have to be very careful on how we split up things and decide how we can put them in.
Yeah, so this reminds me of some previous projects which are software-based. So as you mentioned, like trying to fit a security model into some existing project is really difficult. So essentially, Linux essentially inherits the Unix security model, which was invented in the late 60s, as opposed there was some, you mentioned the multiprocessing work, so it was the opposite of that, and the name Unix was actually even a pun on just doing one thing really well. And also, culturally, it was from a time when people were sharing and they were in campus environments, and the security model was really about stopping people from accidentally overriding high scores in games, or overriding, really probably the most important thing is accidentally overriding somebody's thesis or paper they were writing, but they weren't really thinking about they weren't really thinking about malicious threats and networked environments in the same way. And so trying to retrofit security for the 21st century into a 60s hippie kind of operating system is insanely difficult. And we went through this several times, with just packet filtering, the number of iterations that had to happen in the firewalling. Before NetFilter, there was IP chains, and there was something else before that, I think, and then often there would be BSD would come up with something and Linux would come up with a different version. And so I think BSDs had the same kind of issues. And so SC Linux was a case where essentially research that had gone on, I think, from the 80s into a security model called type enforcement was built around a microkernel architecture, because they were all the rage at the time. And so the SC Linux design today, if you look in the kernel, there's a thing called a security server, and there's bits that still go back to a microkernel architecture. And so trying to retrofit this is really difficult, and it leads to a lot of complexity. People are like, oh, well, these security policies are really complex, but they're just exposing the system. If you designed an operating system from scratch, then it would be, with security in mind, it would look different. So I think that's really important to note, that what we're doing here is retrofitting not just the software, but the hardware as well. So we have to maintain compatibility, even with new ISAs that are coming out. There's still concepts, in reality, we're still having to add security onto the core system. So I think that's a really important thing to note, and realise that there are going to be limitations, and it's never going to be ideal and perfect. And that said, it's difficult. It takes a long time. There are patch sets that I've seen take several years to get through. And I guess what I'd say is, I think it is good for the community. So if you have the memory tagging or the protection keys, you have different vendors and interest groups. I think you've got a foundation coming together and then representing as kind of one voice to the kernel community, for example. We've had issues in the past where Linus really didn't want to try and choose one security model over another, and told the different groups that were fighting to basically, get their act together, let's say. So I think probably this, having the way you're doing it at the moment, I think if you need help, definitely reach out to the community, more senior community, who I'm sure you're connected to already. Because I think one of the issues there is people don't understand the deeper security picture. And particularly a lot of kernel developers are very smart and focused on their particular area, but some of them just don't really care about security in the way that we do, right? So let's just put it that way.
So maybe to continue this one, I think it's not like it is, of course, some cases that people just don't understand the technology. But I, for example, personally don't know how can you argue the benefit of certain security technology when the benefit is not 100%. So it's not like if you have some silver bullet which closes one style of particular attacks, then it's easy to say, okay, here is the silver bullet. Merge this patch set. It's that complexity, that performance, but when these attacks are closed, it's hard to argue. But if it's something which closes some subset, and then there starts to be this long discussion, okay, how much sense it makes, because, it's not a silver bullet, it brings some complexity. You try to argue usually, okay, this is slow hanging fruit, so, simpler attacks are closed. But this discussion can easily go, off to endless discussion and what could be what are the reasons which can really convince maintainers that okay, even if it's not silver bullet, it's still worth it because it brings benefit. It could be protection keys already supported across the vendors, so to have maybe some suggestions of what could be the reasons, or if anyone has suggestions what could be the reasons in that particular cases, how do you position a threat model correctly that it's a bit of benefit or some amount of benefit is better than no benefit.
I think one of the big problems with security that I've found over the years is it's always a compromise. So, you could bring in a new technology, but it's going to affect performance, or it's going to affect code size, or it's going to affect some other aspect of the system. And actually, how do you quantify that? And like you say, it's selling it almost. You need to sell it to the
sell it to maintainers, right?
Yeah. And I think that's a really difficult part to put across. I mean, a lot of the arguments are just, you put the patches down there. You can see the technical side of it, but maybe not the
usually the hardest discussions are not on technical side. When you get already to the technical side, when they're saying to you, fix this or fix that, it's actually doable. You can do this.
Yeah.
But the selling part is hard. But you can also, I can also feel for, maintainers' side, because from their point of view, they probably see the showcase of all these technologies coming and going every year, from all vendors. And if they would be saying yes to every single one, it's also the kernel will grow. Some of these technologies are probably stopped being maintained after a couple of years, so they're runway to something. So I think we're at both sides of the of the equation. So yeah.
And the use case. What's good for one person may not be good for somebody else.
I think on that point it might be obvious, but having buy-in from a clear and important user for a feature will definitely help, because maintainers at the end of the day just don't want to be maintaining code that no one uses, and I think that's maybe the most important aspect. Now, obviously, there's a bit of a chicken and egg situation here. How do you convince an important user to use your feature? But I think this is something happening probably not really on the list, but more backstage. And that's...
But how would you define an important user? So
Well, that's obviously very subjective. But for instance, convincing, if you're targeting more mobile devices, convincing someone like Google that this security feature is useful and maybe you want to use it on Android is
Okay, so basically going to the distros, like would be example, going to the distros and saying, okay, this feature is not an upstream, but trying to convince the distro to turn it on, then to show to upstream maintainers. I think this is Case Cook favorite way to getting hardening, like not hardware hardening, but security features upstream to kind of go with distro route
and I mean, if you look at the history of memory tagging on ARM64, essentially there was a clear push from Google in that case, and that's obviously what helped it go upstream, because clear user. Even though MT has some real challenges in both in the deployment and also some ABI aspects, and it's also not a trivial feature in many ways, but there's buy-in.
Yeah, so obviously the most important user will be Linus with his laptop. So if you can make something that he wants to run, that's really going to be helpful. And I was just thinking there that with the protection keys, if you can demonstrate this is really good for, and I think CHERI can do this as well, as debugging and this may be a thing where people switch it on, run their code, and I think there's some potential there to be able to be selling this as a debugging and code quality feature as well.
I'm going to disagree a little bit with your premise there, Elena. I actually think that there are lots of security features that have been merged without much objection. And they're usually the kind of security features that say, here's a new CVE, this mitigates it. That there have been plenty of those that have created less friction and maybe have a lower bar for tidiness or beauty or being aesthetically pleasing. Whereas if you try to introduce a security feature that is defense in depth, that's hardening or something like that, I think the bar is understandably much, much higher. It's sort of analogous to the difference between publishing in a top security conference a paper that demonstrates a new exploit. Relatively easy to get through the review process, as opposed to, here's a mitigation that addresses some existing class of vulnerabilities. It's not that anyone's asking for this, but we'd like to make an argument that it would present some benefit for the ecosystem. That's a much higher bar to reach. And it's also harder to make the argument that if you're going to introduce something new that's not closing a CVE, you've got to make a value proposition that says, this is going to mitigate maybe a class of vulnerabilities or mitigate all potential threats in some area, as opposed to selecting a particular CVE. I think it's the argument for those features becomes a little bit more obtuse. And so I think you have to look at the nature of the feature, the nature of the threat model, and that could be a guide for how much challenge you could expect to face when taking your feature through the upstreaming process.
Maybe just quickly to reply, I fully agree, because I also thought that like the easiest technologies we have merged is even with some hardware support is all the bug fixes, especially like we think how fast the side channels were fixed. I mean, relatively. I mean, it was pain in many other ways, but still, like, the patches and everything the reaction was pretty fast. So, and keep reacting. So I fully agree that when we have concrete thing and concrete problem, then usually solutions come very fast. But proactive is always more difficult. Okay, so maybe, let's see how much we're doing on time. So maybe we can also open it for questions from the audience. So, and I can even try to run around if people want to ask their own questions to the panel members. So raise your hand.
Thank you. So, would maybe also some regulatory pressure help, for example, via the CRA? So, for example, if there is a standard which says, yeah, well, you have these great hardware security features. They would mitigate some stuff which we regularly see. You didn't enable that, although the hardware supports it. And then you need to actively justify why you have different mitigations addressing that problem. Would that help from your perspective? And would that be a reasonable goal of pushing regulation in that direction?
I don't know if anyone wants to comment on that. I personally don't think that like pushing always helps. So it's like, and I think especially in open source community, so we are not talking about like, that there is some kind of one top level organization or something which can push everyone. So at least my opinion would be, I don't think that would necessarily help. And also how would you push something like this in terms of, you would either have to go into details and specify what exactly type of technology you have to enable, which might not even cover all the hardware, so it would be differences, or you would be very on a high level saying, you have to have some memory protection, and then it's so high level that probably anything existent would qualify, so something like that. So
I agree. It seems very difficult to define this at the regulation level, which also cannot change every 6 months, right? To have something that's quite set in stone for a while. You obviously have some overlap in features between, let's say, ARM64, x86, but I think at the regulatory level, it's complicated. Now, however, what is definitely useful is when governments are pushing for more, let's say, secure by design approaches, to paraphrase, in fact, the UK government push, which was behind the moral of funding, CHERI. So I don't think regulation is necessarily the best way to think about it. It's more governmental incentive, let's say.
I guess where regulation can help is, well, first of all, it increases the visibility of something. So say, for instance, the governments were to come out and regulate memory safety, for instance, something I might have a
good luck with that.
yeah, exactly. I mean, they're not going to specifically say how you would do it. So you could do it by using Rust. You could use a hardware mechanism. Who knows? But that sort of thing could potentially drive solutions. But I think that would be more of a case of incentivizing the IP manufacturers, people like ARM, to put those technologies in because they can see a drive from their customers to do that. But then there's still the interplay between getting it into the kernel, for instance, and getting the hardware there. I mean, what you're doing at the moment with the modeling it and stuff like that, you still have to get the hardware feature and then get it accepted in before people can use it. Yeah. Just justifying something that may be there but isn't usable by regulation, I don't think that would really help.
Yeah, absolutely. And I would just add that you have multiple levels of multiple hurdles here, because first you have to convince companies like ARM or Intel to add to define the feature and add it and so on. But then you also have to convince OEMs to actually adopt the feature and then for the whole software stack to come in place. So yeah, it's you have to push at all the levels, essentially.
It's a complex supply chain.
So I would say that regulations don't work like that. They're not aimed at trying to convince Linus. They're aimed at trying to convince the end users. And someone said earlier on that, if you can find, Google or JPMC or, the World Bank or Motorola, and they're convinced by regulation, that's the way that the pressure comes on. It's not aimed at the techies, like most of us here. It's aimed at the end users, and they're the ones who are able to put the pressure on. And that's why regulation, I think, can help. Standards tend to lag, of course, but regulations tend to lead. So that's where I think there might be some possibility.
Hey, do we have any other questions?
Oh, I just had a kind of a follow-up on that. So I think based on at least the US model, there are kind of standards for government and military based systems, and then there's like programs for assuring that software and hardware systems meet those. So in terms of regulation, I think that has actually had quite a big impact on Linux security over the years. Maybe not in an obvious way, but certainly a lot of the distro efforts around security have been about making their products accessible to meet these standards, and so that certainly has driven certainly some of the security development that distros then hired people to work and or encouraged work that was then done in the community. So I think that has certainly had an impact, although one thing that's interesting is it's still not going to convince some of the maintainers. So there's the FIPS standards that people know, and I think anyone who's worked at a big distro company or a software company has had this like push from the management that you have to get the FIPS stuff done, and then you go to the upstream maintainers and they just flat out say, we don't care about this. Go and pound sand, basically, but probably not that politely. So yeah, I think there's definitely limits to the government certification, but certainly there are, and obviously I think we're kind of overlapping a bit with some of the public safety infrastructure meetings that have been going on, and automotive. There are definitely like domain-specific areas where there are requirements, energy, for energy systems, power plants, and so on. So I think those requirements, in a broad sense, can have an impact.
I'm not going to comment on government regulations.
Maybe it's time to switch topic. So any other questions? So maybe I'll just throw another angle. So when a hardware security feature is being developed, even if it's targeting like, generic use case for security, the way how it's kind of integrates into different operating system, because usually, of course, here we're talking about Linux, but, there are other operating systems in use, and the hardware, runs different operating systems. So what do people think about the challenges of that the feature might fit into a certain operating system better than into another? And if the initial design was done with maybe a bit more focus into one operating system, then thinking it's probably similar in the other ones, and when you try to go and enable it, and you see issues that it simply the concepts are too different, even though you would think operating system concepts are all the same, but implementations differ. So what people think about these challenges of fitting, because we have usually one hardware solution, but different OSs. So could that be one of the factors that we just don't test enough OSs to go smoothly each of them?
Yeah, that is certainly a big complexity for ARM, I think. I would say with Linux it's a lot easier because, Linux is open source and available, and that's something that definitely for new features we think about firsthand, essentially, and it's more and more integrated in how we think about new features. For other operating systems, it's much more indirect. It's more of a case of we talk to the relevant vendor, and then they tell us what they think about it, and we will make the architecture will adapt based on that. But it can be complex, and it can also lead to a situation, unfortunately, where some features are very targeted at one OS, some are much more at another OS, and you can end up in a little bit of fragmentation of security features, which is not ideal, but the unfortunate reality is that some operating systems are also not very flexible and harder to adapt. Not going to give any names.
I think it's actually for any operating system, it's the case. Like, you have to convince the respected, whatever maintainers, architects, designers to, whether your feature kind of should be working this way. And especially like if you're trying to, let's say to them, okay, this way it would work, let's say, simpler, and it would fit these 3 operating systems, but you're asking it to work maybe in that angle, which better fits your operating system, but then the other 2 will have huge issues with it. So, I mean, this also potentially kind of, you can end up in that situation.
Yeah, and obviously if, let's say, if a feature would only be useful on Linux, that would definitely make it a lot less appealing as a potential feature. So, yeah, that's an angle.
Yeah, I mean, we have first-hand experience with this as well. If you have an operating system that is built with a particular security paradigm in mind, say it's capability-based, be the obvious one, then yes, having a hardware capability system is a lot easier to fit in there. If you have something like Linux, which actually has quite a wide range of different technologies in there, then sometimes you are pushing against a model that already exists, for instance, in there. And how you don't want to be shoehorning something in. You want to be creating something that works synergistically with the existing mechanisms. So, yeah, that's something that takes a lot more finessing, put like that, to try and get it in, which does make it harder. And you are changing models that people are used to, which people obviously push back on as well.
I said earlier that there are no corner cases. So now I'm going to introduce a kind of paradox. I think if you operate from a purist mindset that whatever security feature, whatever proactive security feature you try to introduce must be usable by everyone, you're going to have no new security features because you're always going to encounter some constraints that, while they may frustrate you, are essential to having a thriving, dynamic software ecosystem. So one example is Intel introduced control flow enforcement technology, the indirect branch tracking, CET, IBT, several years ago. And we had success upstreaming support into the Linux kernel for CET IBT. It's a forward edge CFI enforcement. It was not possible, or at least it has not been possible thus far, to do something similar for Windows. So Windows has its own software-based solution that they published called CFG, Control Flow Graph, I believe.
Is it God?
It's CFG. Oh God. Okay, I got it. Yeah. Perhaps that's correct. And because there are different requirements, they have lots of legacy drivers from who knows when that can't be recompiled to use the end branch instructions. And if we had tried to design a control flow integrity technology that could be universally deployable, we would not have a control flow enforcement technology. You have to be willing to make compromises. And a very good friend at another company told me something a long time ago that measure the security of a feature, not by its security, but by its security multiplied by its adoption. And so if you can release a feature that's pretty secure and a lot of people are able to take advantage of it, even though not everyone is, that is a very good feature.
I think that's a great point.
Question.
Actually, a very brief point. That's very similar story with memory tagging and Windows. Mm-hmm. Was not adopted on Windows because it doesn't really fit into Windows.
Sorry, the corollary to the adoption thing is that nobody cares about security; they care about risk, and so it's whether something is useful is whether it helps reduce risk at the same time. So I absolutely agree with the adoption thing, but there's another parameter we need to bring in there, and it's not always easy to transfer people's understanding of risk into something that makes sense for us, and that can be really, really hard. But there we go.
But how would you quantify the risk? It's so difficult. Like whenever you reduce to risk and how much it's worth the
risk is it's a really easy. There's a measurement. There's a formula, right? Risk is exposure times cost. Likelihood of something happening times cost. I mean, that is what risk is. That doesn't mean that it's easy to calculate both of those things. I agree, but that's kind of how you need to look at it. And also, humans are really bad at calculating risk and guessing risk and all those sorts of things. So,
I'm just thinking, like, if we can have that kind of simple formula, something being agreed, and when maintainers also believing in it, and when we know, okay, in order to, get this feature in the threat model, we calculate it this way, and when, we have high chances. But I don't think such kind of unified formula would be possible.
Well, everyone. I mean, everyone in business agrees that that's what the formula is. That doesn't mean that that we're going to agree how to apply it. That's the other thing. Risk versus the effort that we think something is worth doing versus the maintenance and all those sorts of things. There's lots of pieces in the and convincing Linus and then convincing Greg to keep it in and all those sorts of things. There's a whole bunch of stuff, but yeah.
I think the other thing with risk is it changes per product. So, everybody has a different view of what in their product characterizes the biggest risks. So how do you agree something that's universal really is difficult?
Any other questions? Actually, almost out of time, but if there's any quick question, we can still take it. Okay, if not, let's thank our panel members.